All right. Hello. Today we are working on Part C of Homework 4 for Transport 1. So in Part A and B, we have already derived the steady state equations for the initial flow rates and derived the differential equations to solve for the time variation of the fluid height in both tanks. And now we're going to write a code explaining how to solve for those initial flow rates. So what we're going to do here is we just import some functions from SciPy, integrate, import, solve IVP, initial value problems. So this is just going to allow us to solve a set of different differential equations, which we'll be doing in our code. And then we want to import SciPy Jack's numpy as J and P. We're going to be using a lot of algebraic functions in our code, in our expressions, so that it's going to allow for that in our code. And then we want to import Jax because we will also be using a switch function to account for some sign changes in our expressions, and import Jax will allow us to do so. Next, we want to define some of our initial conditions that we were given in our problem. So I'm going to go ahead, T end is going to be 2000. We're going to define our area of the cross-sectional area as 1, and for a cross-sectional area for the second tank as 1 as well. And then the area of the first tank is given as 4, I believe. No, 0.2. And the area of our second tank is given as 0.2 as well. Okay, and then another function or variable you want to define is the square root. Our square root times the gravity constant, because we are using that a lot in some of our expressions. And just defining it here is going to make it easier to calculate and run a lot smoother in our code. So we're going to do that by doing J and P square root 2 of 2 times our gravity constant, which is 9.81. All right. Oh, and I almost forgot our initial heights for tank 1 and our initial heights for tank 2. These are both going to be 5 for tank 1, 3 for tank 0. Sorry, I'm very tired. 3 for tank 2, the initial height for tank 2. All right, so now that we have those, let's make sure. Our indexing is all good. So now we're just gonna put in, I'm not really sure what that is. We're gonna put in our expressions so our steady state equations that we derive for the initial flow rates. And that is going to be Q into initial area of our first tank times the height of tank, initial height of tank 1 minus the initial height of tank 2 times square root 2g, so 2 times the gravity constant, times J and P square root, taking the square root of our heights, change in heights from tank 1 to tank 2, so H1I minus H2I. Alright. And so here is where we add our absolute value, because we want to make sure that the change in our heights, if it's a negative change, it needs to be positive under the square root to avoid errors. So we're going to add an absolute value here to come out with positive integers only. And then that's where we need to integrate our, or not integrate, we need to implement our switch function, which is J and P sine, which will account for our sign change under the square root. Now I want to make sure all my parentheses are closed. And then we want to go ahead and put in our equation for the initial flow rate at tank 2, which is going to be the area at tank 2 times the square, or 2 times square root of 2 times our gravity constant times J and P square root of the height at the initial height at tank 2. All right, and so our our two tanks are expressions in a steady state, so that we can for our inlet flows, we can write that the initial inlet flow for tank 1 is equal to the initial inlet flow at tank 2. And then how we calculate that is putting in our expression of Q2 initial flow rate at okay, sorry. So here we're showing our steady state. Here we're calculating our inlet flow for tank 2, and that is going to be the flow rate at initial flow rate at tank 2 minus the initial flow rate at tank 1 in tank 1. And then we're going to use our print function to return our flow rates. Q1 and I. Okay. So we're going to print our initial flow rates for tank 1 and tank 2. I'm going to run this. And we're given some values. And those look good because the initial flow rate in tank 1 is going to be greater than the flow rate in tank 2. So that looks good. Okay, so now we want to create a function defining our right-hand side of our equation. So we're going to do the derivative of our heights with respect to time. And that's going to be our parameters of t and h. H1 for tank 1 is going to be indexed as 0. And the height at tank 2 to be indexed at 1. And then what we want to do is we want to copy our expressions down here. And then, but we don't want them to be the initial. So we're going to get rid of all of those. So now we want to actually calculate the heights, the resulting heights, and flow rates. Get that off. All right. Let's make sure we have an indent here. Not this time. We're having an error. Huh. Alright, Google just deleted my code and I'm not really sure how to get it back. So we're just gonna rewrite this, define the derivative of our height with respect to the time, parameters of time and height. Each one is going to be indexed at 0 for tank 1, and each 2 is going to be indexed at 1 for tank 2. Alright, so now we're going to copy again our expressions from up here, but this time we're using our height of tank 1 and our height of tank 2 and not our initials, so we're going to get rid of all of those little coefficients and change that. I want these to line up just to have my code run smooth. And then we will return an array of our flow rate in tank 1 minus our initial flow rate in tank 1 minus our flow rate at tank 2 divided by the cross-sectional area of tank 1. And then for tank 2, we do the same thing. But we're going to add the flow rate of tank 1 and subtract the flow rate of tank 2. And then divide all by the cross cross-sectional area at tank 2. Alright. Oh, that doesn't go there. Okay, I don't know, excuse me, sorry. Not really sure why it's not turning my... Maybe sometimes if you run all, it'll work. Yep, looks good. Okay, so let's check it real quick. Okay. Let's check that our functions and our expressions are working. So Q2, initial flow rate for tank 1. Looks good. And then the initial flow rate for tank 2. Yeah. 2I. Looks good. Okay. Alright, so next we want to solve for our differential equations for the time variation of the fluid heights in both tanks. So we're going to define that as a result for our solve IVP of our right-hand side function. 0, 10 at the end. We want our heights, initial heights of tank 1 and tank 2. Using a Rideau method. Set our condition to true. Actually, okay. So we're getting values for this, but we need to actually go back here and define our Q12 and Q2, which are our flow rates for tank 1 and tank 2. So do that by finding Q12. We want to return the time, our initial flow rate of tank 1, 0.8 times, or 0.8 times our initial flow rate of tank 1. And then we're going to define our initial flow rate for tank 2. Time, and we're going to return time, initial flow rate for tank 2, 1.2 times initial flow rate for tank 2. And some arbitrary numbers. That looks good. Put that into our code. We also need to define our switch function. For T, our volume in tank 1, our volume in tank 2. Call it T switch, time switch, and give it a scale. And we will return that using the sigmoid function. Sigmoid function T minus T switch divided by our scale times volume in tank 2 minus the volume in tank 1 plus the volume at 1. Make sure indexing looks good there. Okay. Great. So now we can run all. It all looks good. And then next thing we want to do is we want to start solving for our flow rates. So for our result, we're going to solve our initial value problems. And find what's our right-hand side of our equation. Where we stop from the beginning to the end. Our initial heights at tank 1 and tank 2. Using our Rideau method. Setting condition to true. Alright, now we want to plot our time. Okay. Alright, there we go. 19 plot. Close JMP. We're going to use linspace for start and stop. So we're going to start at the beginning and then the time where we stop. And then go to 5:01. Calculate that last time for the flow rate. And then for our solution, we solve the flow T-plot. Okay, we have some errors here. Okay, we're gonna going to not really sure what the error is here. missing parentheses. Alright, I'm not sure what is happening here. Unsupported operand types for tuple and device array. So it's telling me to look here at my array. And let's see, maybe I'm just not really sure. Maybe I'll just get rid of that and do no, it's not working either. Okay, I'm just gonna rewrite it because sometimes that works as well. I'm just gonna redo this up because sometimes that's all you have to do to get it to work. Okay, I'm just gonna keep moving forward. I'm hopefully plotting my graphs well. I'm gonna fix the problem. At this point, I really truly give up. Import mix of plots. Import plot graph. Let's go so we can choose what kind of graph we want to represent our data. And okay. Alright, so now we're going to start graphing. So our figure makes subplots. We'll give it one row, one column, trace. I'm going to choose a scatter plot. Our x-axis is going to show our time plot. Our y-axis is going to show, hopefully, because our stored functions have an error, but we're going to see how that works. I'm going to name it, this is for our heights, I think 1. For row 1 in column 1. Okay. The two plot is not defined. Okay. It's just not working. I don't know why. Alrighty. I'm really not understanding my error here, so I might